The last part of section 2.9 deals with transforming absolute value functions and graphs. And what I'm going to do is I'm going to do on the first screen here 3 examples on the same graph so you can see the effect of such numbers when they're added or subtracted to the absolute value equation. Now, the first one is the parent function, which I'm going to do in blue. I'm going to color code everything. And if you'd like to pause the video, please do to copy this down and restart when you're ready. But otherwise, I made a t-table of x equals -2, -1, 0, 1, and 2. And I'm just going to plug these into my equation. And obviously the absolute value of -2 is 2, the absolute value of -1 is 1, absolute value of 0 is 0, and so forth. And so what I get is my absolute value parent function graph, which I described in the prior video. And all transformations are transformations of the parent function, which is what you see right here. And the key point is the vertex. The vertex is the key point that we want to pay attention to throughout this video. All right, now I'm going to do a little fixing of my word here. Okay, now let's talk about the second one, the one that's in red. Y equals absolute value of x minus 2. If I plug -2 in for x, I get -2 minus 2, which is -4, which turns out to be +4. If I plug in -1 for x, -1 minus 2 is -3, which turns out to be +3. If I put 0 in there, 0 minus 2 is -2. It turns out to be 2. And if I put 1 in there, 1 minus 2 turns out to be -1, which turns out to be +1. And 2 minus 2 turns out to be 0. I'm also going to put a few more pieces of data in there. Let's try 3 and 4 just so we have some comparison. If I put 3 in there, 3 minus 2 is 1, absolute value 1 is 1. And if I put 4 in there, I get a value of 2. Now, what I'm going to do is I'm going to plot these points that I'm putting in the box. 0, 2 is right here. 1, 1 is right here. 2, 0 is there. 3, 1 is right there. And 4, 2 is right there. And if I draw my graphs, it should look something like this. Now, the key is what happened between the blue graph and the red graph. What is the effect of the -2 inside the absolute value? And if you notice, the two graphs should look exactly the same. However, it is slid to the right 2 spots. So the effect of any number inside the absolute value is it moves the graph to the right or to the left, depending on what this particular symbol is. Let's look at the third one, which I'm going to graph in green. Y equals absolute value of x plus 3. I made a t-table, and if I put my numbers in, if I put -2 in there, absolute value of -2 is 2, plus 3 makes a value of 5. If I put -1 in there, absolute value of -1 is 1, plus 3 is 4. If I put 0 in there, obviously the answer comes out to be 3. If I put 1 in there, 1 plus 3 turns out to be 4. And if I put a 2 in there, absolute value 2 plus 3 makes, off my chart here a little bit, this would be 3, this would be 4, and this would be a 5. Sorry, having a little difficulty staying on the board there. But you get the idea. Now, if I plot my points, -2 is up at 5. -1 is at 4. 0 is at 3. 1 is at 4. And 2 is at 5. And so my graph looks like this. And again, I want to compare it to my blue graph. Well, what happened? What happened is the vertex, which is the key point in the green one, went up 3 spots. And that is the effect of any number that is added or subtracted on the outside of the square root. That particular number makes the graph move up or down. Now, to summarize that, if you want to pause the screen, go ahead. But otherwise, I'm going to fast forward one slide. And here's your notes for the general form of an absolute value function. If you notice in the green box, this is the general function, y equals a times absolute value of x minus h plus k. And I color-coded the a, the h, and the k. And they match up to the information at the bottom of the screen. Now, number one, as I just showed you on the prior slide, the h value moves the graph left or right. And it moves opposite of what you think. If the h value is negative, it moves to the right. If it's positive, it moves to the left, just like linear functions did. The k value moves the graph up if the k value is positive, or down if the k value is negative. The coordinate, if you put h and k together as a coordinate, that is actually the coordinate of the vertex of the absolute value graph. And the a value, which we haven't talked about yet, the a value out in front is the same as the slope of the line on the right side of the graph. And just like linear functions, it deals with stretching and compressing. It will stretch the graph if the absolute value of a is greater than 1. It will compress the graph if the absolute value of a is between 0 and 1. And that is how you can determine what the graph looks like without actually making t-tables and coming up with points or coordinates. A, the number on the outside, when you multiply by a, stretches or compresses the graph. The h on the inside and the k on the outside tell you which direction the graph moves, left, right, up, or down, and together they make the coordinate of the vertex. Now, let's practice that information. If you need to pause this screen, please do. Otherwise, I'll do a couple of examples for you. Okay, example 1. How is the graph of the parent function y equals x, this is the parent function, transformed by the equation in the green box? Well, very simply, if you notice, our h value, h is equal to -5, and the k value is equal to -2. So therefore, h will move, since the h value is negative, it will move the graph to the left 5 spots, and the k value is negative, so k will move the graph down 2 spots. The coordinate of the vertex is -5, -2, the hk values. And finally, the slope is equal to 1/4, which is the a value, so it will compress the graph by a factor of 1/4, which makes the graph move closer to the x-axis. If you need to pause the video, please do and copy that down. This information in the red box is what you would write if they ask you what is the transformation of the graph. That's the information that you want to be able to state. Now, I'm going to graph this, and we should not have to make a t-table anymore because the whole key is where the vertex is. The vertex, as we talked about just a second ago, the vertex is at -5, -2. So I'm going to go to -5, -2, and I'm going to put a dot right there. That is the whole key to this problem. Because now everything starts from there. Now all I got to do is look at the slope. The slope is equal to 1/4. So from that dot, I go up 1 and over 4, and I put a dot. Now that is the positive side of my absolute value function. Of course, the negative side would be negative a, so the slope on the other side will be negative 1/4. So here I'm going to go up 1 and over 4 the other way because I know my function has got to look like the letter V, and therefore my graph should look like this. And if you notice, the graph widened out. That is the graph of this transform function, and that is how you graph without the use of a t-table. Last, let's write the absolute value equation that have a vertex of 2, -1 and a slope of 2/5. Well, if you recall from the earlier slide, the general form is this. So all I'm going to do is I'm going to put my slope of 2/5 where a is, x minus, I'm going to put my 2 in for h, and I'm going to put my -1 in for k. And if I simplify that, I get y equals 2/5 times the absolute value of x minus 2, and then adding a negative means minus, so -1. And that would be how I develop or come up with my absolute value equation based on any given transformations. If you have further questions about this video or the content of this video, please make sure you ask during class. But otherwise, that wraps up section 2.9 and all of Unit 2.